Thanks again to everybody for joining. This is going to be treated as a panel and a line of speakers. You are welcome to unmute yourself and directly ask questions during the presentation. We're happy to have this and would like for this to be an interactive session. At the end, there's a few other items that Safely Share, who is sponsoring this event, would like to share with you. So we will touch upon that at the end. But to start with, I will kick it over to John, and he can start with the introductions. So John, take it away.
Hey, thank you very much. Appreciate it. Hello, New England. It's weird talking to all of New England here. I'm John Kindervag. I'm an advisor for Safely Share. I've known Shamin and Cynthia for quite a while now, and I'm the creator of Zero Trust. So love it or hate it, I'm the guy who started that whole movement. My day job is I'm the chief evangelist for a company called Illumio that does microsegmentation for Zero Trust. And all I do all day long is talk about Zero Trust, think about Zero Trust, and design Zero Trust environments. And when I had an opportunity to come be an advisor here at Safely Share, I was really intrigued, especially given the background of my esteemed colleague, Shamin, who I want to introduce, or have him introduce now, because he's got a lot of experience in the stuff we now call AI, which had a different name back in the day, didn't it, Shamin?
Yes, it did. It was called expert systems or knowledge-based systems at that time. So thank you, John. I am Shamim Naqvi. I'm the CEO and one of the founders of Safely Share. And I'm very glad to be joined by John Kindervag and Ann Anderson of CBS here as well. And she'll be speaking in just a few seconds. Just a bit more about my background. I am a ex-Bell Labs engineer, spent a number of years in the Bell system doing research at Murray Hill, and then did a few startups in the New England area. Currently, I'm based in New Jersey, and looking forward to having a good discussion today with my esteemed colleagues. Ann?
And before we go over to Ann, we should, because you just mentioned Bell Labs, I think we need to acknowledge that one of the big names in technology passed away last week.
Yes,
Mr.
Arno Penzias.
Arno Penzias.
He was the VP of research when I was there, and wonderful person. Used to come very early to work in the mornings, around 5 or 6 o'clock in the morning, before his staff showed up, and he would typically have one of the researchers come and talk to him for an hour in the morning before his secretary showed up. And he always had coffee and bagels with him. So I had the great opportunity once or twice to go and visit with him at like 6 in the morning, which is a chore, of course, to wake up at 6 in the morning and go and talk to a smart guy like that. And we would talk about physics, or we would talk about computing and machine learning, artificial intelligence, etc. And he'd feed you bagels, and then he would kick you out of his office around 8 when his staff showed up. And he went back to his normal day job at that time. So wonderful person, very perceptive. Lots and lots of stories about him and the work that he did. Sorry to hear about his passing.
No, yeah, no, me too. And I got to meet him just once during Bell Labs, but he won the Nobel Prize in physics one year, and very less. Without him, we could honestly say that we might not be here today, right? So,
yeah, no, wonderful person. Used to work out of a Bell Labs location called Crawford Hill, which had the radio antenna. And the most and the story that gets told most often is that he and Bob Wilson were working on sort of eliminating a certain noise in the circuits that they had found, and they did their level best to get rid of the noise, and to the extent that they thought that maybe some bird poop was causing the noise, and they would literally went out and cleaned the bird poop off the radio antenna but it still didn't work, and they still got the noise. So I I used to think that the story was made up. So I actually asked him once whether the story was true, and he said, "No, it's true. We actually went and cleaned out the bird cry."
Sorry for interrupting, Anne. You should take it away now.
That's a great story. Thank you so much. So, good morning, everybody, and thank you for joining. My name is Ann Anderson. I've been in the industry for about 30 years. I've worked for a variety of places, and I've owned two small businesses myself. I also was a member of ISACA for a number of years, having received my certification in the governance of enterprise IT back in 2015. And I found that to be a very valuable certification. And I think what I bring to the table here is a couple of things. So I've worked managing machine learning projects. I'm in analytics engineering and do a lot of data engineering as well. So I have a solid background in engineering and managing systems. But I also have worked very closely with auditors. I know many of folks in ISACA are auditors, and really understand what it takes to dive into a system and make sure that it's in compliance and be very careful about providing evidence and adhering to regulatory requirements. And thirdly, I also have experience with healthcare. So from the support mechanism from IT, really understanding a lot of the very strict compliance requirements that we have to adhere to. And so I hope that I can help you understand how valuable these clean rooms are that Safely Share is providing. And I have been acting as a technical advisory on the board for Safely Share for several months now.
So, John, you in some sense are the logical place to start because you, as you said, you are the founder of the Zero Trust movement and the concept of Zero Trust. Perhaps you could start us off and tell us some basic ideas about Zero Trust and how one should think about the Zero Trust concept.
Absolutely. Thank you. So Zero Trust began as a project in 2008 when I joined Forrester Research as an analyst, and I spent 2 years doing primary research because the big question is, why was cybersecurity failing? And the answer became that we had this broken trust model where systems on the inside of the network were trusted and therefore had no policy attached to them, and system outside the network were untrusted. And so it was assumed that was good enough, right? So we used to say we want our networks to have a hard, crunchy outside and a soft, chewy center. And my first report in 2010 was called No More Chewy Centers, introducing the Zero Trust model. So Zero Trust, first and foremost, is a strategy. It's not a product. It's not a technology. It's a strategy designed to resonate up to the highest levels of any organization, yet it can be tactically implemented using commercially available off-the-shelf technology at whatever level that technology exists. And so Zero Trust purposely decoupled the strategic from the tactical because I knew the strategy wouldn't change, but the tactics always would. And as the gentleman, the military officer who I worked with after he became a consultant at TI, taught me, almost everybody confuses strategy and tactics. So we're so consumed by products that we don't ever get into that higher level strategic thought. And that's what Zero Trust is trying to do. That's why it's become a global movement where you have the President of the United States issuing an executive order. Australia has issued some guidance around it. I just saw today Germany has as well. So it's a global movement, and it does a couple of things, right? It's designed to stop data breaches, and data breaches aren't somebody getting into our network. That's actually the definition of an intrusion. A data breach is when data that is sensitive or regulated by people like GDPR, CCPA, PCI has been exfiltrated, taken outside of our networks or systems, wherever they're located, and they reside in the hands of a malicious actors. That's when a breach happens. And a breach is the only thing that IT can do to get the CEO fired. And if there is a breach, you allowed it to happen because all bad things happen in the allow rule. You had a policy somewhere that allowed a breach to happen. And the other thing that Zero Trust does strategically is it stops other types of cyber attacks that might not result in data breaches become unsuccessful. So there's only two types of attacks. There's successful attacks and unsuccessful attacks. And we can never stop the attacker from attacking, otherwise we'd have to be the attacker. But what we can do is make the attack unsuccessful. So those are the two main goals. And what we do is we invert the process of cybersecurity. And instead of focusing on this big perimeter and the trust model and managing the attack surface, we talk about what we need to protect. So the reason we're doing cybersecurity is because we're protecting something, right? We used to call it information security. I don't know if you're old enough to remember those days before we decided we wanted to be hip and cool, like we were, in some sci-fi novel. But information security was a bigger term because we were securing the information. And so we need to go back to that. So Zero Trust focuses on figuring out what data or assets we have, putting them into a thing we call the protect surface, which is the inversion of the attack surface. And we can reduce the attack surface down orders of magnitude to something very small and easy to protect, called a protect surface. And then we put policy and controls adjacent to that protect surface so we can stop data breaches and we can make other cybersecurity attacks unsuccessful. It's actually very simple. A lot of people who write about it and talk about it make it sound very hard, but here's the secret. They've probably never done it. So to them, it's an academic exercise. And I'm not an academic. I started out as a network engineer, security architect. Then I became an analyst. So, unless you've almost frozen to death inside of a data center with a console cable connected up to a router or a switch, you probably don't have the experiential knowledge to really be in cybersecurity because you cannot learn it in school. You have to do it. Cybersecurity is experiential. It's much closer to carpentry than some higher level thing like physics or even machine learning.
Terms are fighting words, John.
No. I mean,
a lot of the experimental physicists would actually agree with you to say you can't learn experimental physics. You have to do physics.
Right. Yeah. And there's a lot of physicists in cybersecurity, oddly enough. It attracts them because what is our business except zeros and ones is represented by electrons or photons moving around? What are the good electrons? What are the good photons? That's the question we're asking.
And, at the start of this conversation, I had mentioned Arnold Penzias and Bob Wilson climbing up the horn antenna and cleaning out bird poop. So people have to learn how to actually do things.
There you go.
So we have this wonderful idea, this wonderful concept, as you said, of zero trust, and shrink the attack surfaces to some manageable size. And then we have this phenomena which had been going on in the background for a long time, called machine learning, AI, etc. And what we're discovering now is that if you practice machine learning, if you're doing machine learning, if you're building artificial intelligence systems, you are rapidly expanding the attack surface. So it would be interesting to note how we could start a conversation, and perhaps we could bring Anne to this idea and to this conversation now and ask her, what is your experience of machine learning from a threat perspective, and what sort of threats do you see sort of emerging in the machine learning landscape?
Thanks, Shamim. Yeah, happy to try to explain this to folks from my perspective. So I'm going to start with something that John started with a little bit in his introduction, which is microsegmentation. So he used the crunchy on the outside and soft on the inside I've always used the Oreo cookie analogy, so I'm sure you're all familiar with Oreo cookies, which again, it's the same sort of thing. It's crunchy on the outside and it's soft on the inside. And the problem is that a lot of the attacks that come are from within the company, especially when you work for a very, very large company. You know, you have to break apart or micro segment your network into little teeny weeny segments, and then you can protect each segment and only let certain activity in. So that can be done in an ideal world, but given the size of a very large network, that can have its own challenges as well. So as you all know, there's also authentication and authorization, who you let into a database or a system, and then authorization, which is what can they do once they're actually in. So all of those three things can be done to try to secure a system. But as we all know, there can be people who leave the company or people who move on to a different job who retain their access that they had in their previous job. And that is a big problem, right? A lot of the audits are just simply who has access to what and have we remediated that access when it's no longer needed. So the beauty of zero trust is just what it says. And let me draw some very, very basic, simple, fun analogies to try to drill home the point here. I have three little analogies I'd like to share with you. Let's say you want to go out to dinner tonight and you want to select a restaurant that has a certain type of food, a certain location, and maybe a certain price point. You might put that into your Google search engine, and if you do your prompt correctly, it might come back with some recommendations for you for a Mexican restaurant that's close by and, you know, is middle of the road price wise. So did you have to look at any of the data? No. Did you have to see or get authenticated or authorized for any of the data? No. Did you actually have to create that model in order to do that assessment? No. And really, none of that matters to you because all you wanted to know is what restaurant meets your needs. So you have just provided the information, used the data owned by somebody else, a model that may or may not have been created by you or another person, and you've gotten the results that you want. So similarly, say you want to buy a car, there's a lot more variables involved. You can put your questions in, your desires in, and you can use data across safety protocols, cost points, repair bills, and you can get the results that you want without having to see the data. So you don't have access to the data, zero trust. So same thing for healthcare. You could theoretically use a set of data owned by somebody else, and you could begin to understand some of the ramifications for certain groups of people or demographic groups of people. So maybe you want to try to figure out what group of people would be good for getting screenings in a certain area or zip code. So you can use data sets, you can use predefined models, or you can create your own models, and you can get the results that you need for your business. So in this way, it's zero trust. You're not accessing the data, you're not seeing the data, and we're protecting the data very carefully, but still allowing the use of the data. So I hope that helps explain a little bit in more fundamental terms what zero trust means.
And to pick up on that, Anne, right? The big problem is we allow too many people to see or to have access to too much data just because that's the way we've always done it, right? And you know, what happens if an attacker gets past this trust boundary, they become an insider. So all attacks are actually inside attacks, whether they start on the inside or they start on the outside. And so currently, the model to pick up on your metaphor, your metaphor string here is I'm sitting on the couch with my wife watching TV, and I see some dude rummaging through my fridge, and I go, "Honey, do you know who's the guy looking through our fridge?" And she says, "I don't." And I said, "Well, since he has the ability to rummage through our fridge, I guess he belongs here. So we better make up the guest room. Can you go get me a fresh set of sheets? I need to change the sheets on the bed in the guest room." That's what we do all the time today because we don't actually do the things that we say we're going to do. We don't do, any kind of need to know privileged access management in reality. The reason, I call them the Beyonce and the Rihanna of cybersecurity, Snowden and Manning, were able to be successful is once they got on what's called the high side network of the government, they got access to everything on the high side of the government. And that shouldn't happen. And people know that. But in their mind, it's too hard to figure out what data we have and who should have access to it. So, Anne, as somebody who manages data in your company, how hard is it to figure out what data you have and who should have access to that? Is that an insurmountable challenge, or is that something that you feel is solvable?
Well, I think it's definitely solvable, but it is a challenge as well. So there's a variety of mechanisms that we use or we can use in order to see who should have access to what data. Things are very tightly controlled, as I'm sure a lot of the folks here who work for or who are part of ISACA as members understand. So we watch very closely who has access to what data. We're bound by legal contracts across the board, various types of customers. So it's a really, really big deal. So the beauty, again, of zero trust is that the access control problem goes away to a very large extent, and it more becomes a problem of the model. So the machine learning algorithm and the model that's being created in order to return the results, that becomes, I believe, the next focus area that auditors can get involved in and should get involved in right from the start. So rather than taking a back seat and letting data scientists create models to predict outcomes based upon sets of data, the auditors should get involved to really understand what's going into that machine learning algorithm, to understand and weed out any bias or any use of proprietary information that shouldn't be used. It's important to understand how the algorithm works, at least to a layman's perspective, so that you can understand what the outcome is and to make sure that it is in compliance with the laws and the regulatory requirements that we need to uphold.
That seems like a heck of a challenge. Let's bring in the machine learning expert, a guy who has a PhD in this. And Shameen, give us some insights about how all these buzzwords we're hearing, big data. We started with big data, and then it went to, and we had expert systems, and then it went to AI and machine learning, and now we have LLMs, generative AI. We got a lot of buzzwords in this space. Can you kind of help with that?
Yes, yes. So let me start by, and I'd like to pull the strings on one of the metaphors that Anne used, the restaurant example. So suppose that we are sitting at home and we decide to go out, and following Anne's example, we pose a question to a search model to find a restaurant that meets our requirements. So one possible line of attack would be that some malicious agent finds out the street address of the restaurant that has been proposed to us and knows the route we are going to take and decides to waylay us on the way back from the restaurant late at night. So that is one possible threat model. Another threat model a second threat model is that some malicious agent has managed to tamper with the model itself, and the model returns an answer, and a fake restaurant located at some remote street address where there is no restaurant, but guides you to a deserted part of the town, so you can get attacked at that deserted spot in the middle of nowhere. And the third is the model deliberately has been tampered with to return a biased list of restaurants, perhaps with a business interest, so that most inquiries that people have about restaurants are sent to a select few restaurants itself. So there is a bias in the end. These are three types of attacks, and they could be due to either what is known as data drift, in which case the data that is being provided to the model during the training purposes exceeds certain statistical parameters, or the performance of the model has been the subject of some drift, and there is a decay in the performance of the model, or thirdly, that the model has been compromised and there is a bias built into the predictions of the model itself. So how do you protect against these? How do you actually know that the set of answers that you're getting is coming from the model itself? Well, the blockchain world first tackled this problem of how do you ensure trust in a set of responses? And the basic idea was that you have a consensus algorithm. If the majority of people or users decide on an answer, then that is taken as the correct answer. There are also mathematical techniques that were discussed in that particular sphere called the zero knowledge proofs that essentially assure that the set of answers being returned by a model or a program can be trusted, that they are actually the output of the model and not of some spurious other model that is pretending to be that model. But there are difficult computational problems associated with that. The new set of techniques that are being discussed in the literature today is this notion of confidential computing. In confidential computing, the basic idea is, can you trust the machine on which you are running your work? And the trust starts at the hardware level. So this is in some sense saying that the executions being done on the machine are hardened through a set of encryption techniques that allow the workloads to be encrypted in transit, encrypted in store, and encrypted during execution itself, so that only authorized, authenticated entities can access the memory contents of the machine, and the executions are protected by the machine itself. And the machine certifies and produces an audit log that only authorized entities that passed the cryptographic tests were allowed to interact with the workload and provide input. So the notion that large language models can be fed data through certain tokenization and data de-identification techniques is being discussed in the literature now. And there are some companies, startup companies, etc., that are actually providing systems that allow encrypted inputs to be filtered before they are sent to large language models. And sensitive information is replaced by tokens, so that the large language model itself does not know the private and sensitive information that is being used in the computation itself. So that's, I've gone very quickly through a lot of stuff, but basically those are the kinds of attacks that need to be addressed. And this notion of zero trust needs to be extended to sort of include the use of generative AI models, and we are now talking in terms of model security, data security, encryption techniques, controlling and filtering the inputs to these large language models, and trusting that the model has not been tampered with, that is producing a set of responses.
So it seems to me, oh, go ahead, Anne.
All right, thank you. It's so interesting. I love to listen to Shamim talk. So many great ideas and such deep knowledge. From my time in audit response, I can't help but try to put myself in the perspective of the folks on the phone who are auditors, trying to make sure they understand what their job is and what their job is going to be in the future. And I'd like to, tell a little story, if you don't mind, about some work that I did. And I think you're going to be able to understand how to identify false positives and false negatives through this example here and convert that into auditing of models. So one of the projects that I worked on was machine learning for infrastructure health. So what does that mean? We were very heavily in the back end platform for a lot of the servers, the storage arrays, the network devices, the switches that connected everything. And as you all can imagine, sometimes those things fail, right? The infrastructure dies, there's a problem, it fails. It could even be due to a security hack or a breach. So one of our goals was to get ahead of the failure and understand when things were starting to go downhill before they actually failed. So what we did was we set up an infrastructure machine learning health engine where we track the behavior or the health of these various infrastructure components over a long period of time, like many months, 6 months to a year. And then we compared that through machine learning with their current behavior on a day-to-day basis. And what we were able to do was to identify anomalies in the health of those components. And what we found was that there were many, many anomalies. So we were generating hundreds of anomalies every day, and it was too many anomalies for people to actually look at. So we decided to overlay that with a rules engine. And with that rules engine, we had to talk with the engineers in order to understand what were valid anomalies. So they, if we had too many anomalies, there were too many false positives, and we needed to really narrow that down to the most important ones. So bringing this back to today's subject, if I were an auditor and I needed to go in and understand what was being produced by some of these machine learning algorithms and models from various sets of data that nobody can actually see, it becomes an exercise of validating the results. And really, just like you do with all of the other auditing tasks that you do, picking and choosing some things to look at and sampling the results and finding if there are too many false positives, some false negatives, which will help lead you to understand if there's bias or something else that's wrong with the model that can be then tweaked in order to get around that and produce more valid results. So I hope that helps explain it a little bit what I would think you would need to do from an auditor's perspective, along with using the COBIT, framework that ISACA puts out to define the various things we need to adhere to. So John, thank you. Passing it back off to you.
Yeah, it seems to me now as we get into this discussion, and I'll ask for you and Xiaoming to pick up on this thread, as we're talking about threads today, that there's two distinct challenges here in cybersecurity related to machine learning. One side of the house is very worried about attackers being able to use machine learning to make much more sophisticated attacks that we can't stop. And the other side of the house, which is where I tend to sit, is that we can use machine learning to analyze the data and figure out whether the traffic is good or bad, validated or unvalidated, whether we should have confidence or not, and whether we should allow it to come in and access the resource. So I wanted to, and maybe there's more things that fall into that, but and then of course there's greater societal things, like who's using what data is being imported into these large language models. We see lawsuits from people like New York Times saying people are illegally ingesting their intellectual property. We saw the strike of the writers in Los Angeles, primarily about generative AI and having a computer write a script instead of a human being. So those are societal issues, but from a cyber perspective, you're looking at it from the attacker perspective or the defender perspective. Shameen, do you have any thoughts on that?
Yeah, and there is one more thing that I wanted to add to the list, which is when can somebody who is getting a response from an AI or a machine learning model, when can they trust that answer? Or should they be able to trust that answer? So that's another threat model.
Well, in zero trust, we never use the word trust. That's the T word. So that's the
Yeah.
four-letter word.
What?
What we're trying to do is validate, right?
Yeah.
Validate something using multiple inputs so that we can have confidence. Confidence is a better word, right? So if you go back to the history of trust, trust is a concept that primarily existed in the world of philosophy and religion up until the 1950s. And then in the 50s, we started talking about it in workforce, and that the guy's name was Morton Deutsch, who defined, and this was long, I didn't even discover his research until 2 years ago, probably, but Deutsch said something that really resonates with me. He says, trust is the willingness of one person to be vulnerable to another person. And I've always said trust is a vulnerability in cybersecurity. It's a vulnerability that's exploited by malicious actors because all data breaches are ultimately the exploitation of trust. So we're asking, to what degree of confidence can we have in a system? Because confidence we can measure. Trust, I would argue, is binary. It's,
No,
it's,
that's John, I completely agree with you. Let's not use the word trust. Let's say
yay.
what is the confidence I have in a set of responses returned by a large language model. So for example, we know this concept of hallucinations. The model makes up things, right?
And isn't that true?
Right.
I mean, I
So
have experienced that myself. I'm like, where did you get that? So,
okay. So I mean, for example, my son, when he was very young, would give me answers that he had seen that were coming straight from a Google search engine, and I would say to him, "Why do you think that this answer is correct?" Because he said the search engine told me that, and I went to great pains to sort of explain to him this idea that search engines are essentially based on a large number of opinions that people have about some topic, not the fact that there is some truth serum uh, that is being used to calculate an answer. So it's not mathematics. It's a set of opinions, and it's a majority opinion that is being told. Right. So how do we? So anyway, let me go back to answering the question itself. The basic technique that I think is rapidly going to become a part and parcel of machine learning practice is this notion of runtime encryption and runtime tokenization. I think that it's going to be practically used to filter and tokenize inputs that are being provided to large language models. I think that models themselves would be deployed in an encrypted fashion in protected environments so that the confidence level that one attaches to the responses coming from the model and the data that is being fed into the model is very, very high. And the notion of confidential computing, the notion of zero knowledge proofs, the notion of homomorphic encryption, etc., all of these techniques essentially are contributing to increasing the use of encryption in machine learning systems.
yeah, and I would say I wrote a report at Forrester called "Kill Your Data." The idea that the only good data is dead data. So the killing data technologies are masking tokenization and encryption, right? You want to have your data so that it's dead and it can't rise from the grave and come back to bite you. And so I would love to see a time when we have more data encryption happening more ubiquitously, still being used, and there's ways to do it that you can still use it in search and everything like that. But it comes into conflict. I remember there was a company I won't say their name, but when I wrote that report, they were all over me because they their their model, they deduped data in the public cloud. So if you and I both read the same report and we wanted to save it in our cloud storage area, they would know that, okay, you both have the same thing. So we're just going to give you links to the same data set, but we're only going to store it once. And they said, if we start encrypting it, then do you realize the costs of storage that are going to encrypt for us, that are going to increase for us? And I said, not really my problem, right? Because how do you know whether that's something that should be shared or whether that's something that's highly confidential and sensitive? And they said, we don't. We just know, by hashing that it's the same file. So I would argue that we absolutely have to go down this road. I think you're right on.
Yeah. No, I mean, I can tell you that when I speak with certain potential customers, one of the questions that I am most often asked is, okay, you are trying to sell us on this notion of data encryption. What does it do to the latency of my computations? And I often say to them, it depends on how much you value the notion of having confidence in the computation itself or of protecting your computation. There is a cost, of course, associated with the use of encryption. It's not free. There is no such thing as free computations. So yes, but are you willing to pay the cost of a breach? And if you can protect that, then a little bit of loss in the latency is perhaps acceptable.
What's your view there over at CVS? I'm asking this as a customer who has to go over to my local CVS store today and pick something up. So, Anne, make me feel good.
Oh, you should feel good. We have very, very strict encryption and protection. I actually have a strong background in integration engineering, and the use case is a little bit different for the clean rooms than the zero trust, and it does take an additional vendor or two to make this connection. But imagine this. You've got a pipeline and you've got many endpoints in that pipeline along the way. And every time you have an endpoint or a handoff or a handshake to another vendor, you run the concern that you could have an error or a problem. So there's a great value in clean rooms with respect to consolidating and simplifying the pipeline, so to speak. So imagine instead of going from point A to point B to point C to point D to communicate and then getting information back to make sure a prescription or something like that was successfully delivered, written by the doctor, delivered to the pharmacy, picked up by the customer, and then the claim went in and all of that. Imagine if that could all be simplified into the shared use of a clean room, if it was properly secured. The data can be, we talk about zero trust with not sharing the data and only using the model in order to get the results out. And that's one great use case. But another great use case is actually allowing certain folks, who are properly authenticated and authorized to have access to certain types of information within a shared location. And it actually streamlines it and makes it much faster. I know that I've gotten to a pharmacy before and I had just run from the doctor's office. Maybe I've got poison ivy and, I'm very itchy and I definitely need my prescription right away. And then I'm told, oh, well, we haven't gotten that yet. You're just going to have to wait. So you wait and you wait. So speeding things up, making sure they're secure, reducing the number of handshakes or handoffs along the data integration pipeline. All of those things can be benefited by the use of a clean room, especially with the very strong security that's overlaid on top of that.
Yeah, no, it's the notion of data clean rooms has been around for some time. The one thing that is new in the realm of data clean rooms is who has access to the clean room. Does the clean room provider have access to the clean room also, or only the parties that can use the clean room have access. So let me give an example. In the safely shared clean rooms, safely shared does not have access to the clean room. If we create a clean room between CVS and a pharmacy customer, then only those two entities have access to the clean room, not the fact that safely share is brokering the clean room in that sense. So in that sense, there is no other party that has access to the clean room. It's a fundamental shift in terms of the technology. The clean room only has authenticated access, and the provider of the clean room does not have access.
And it's actually pretty exciting because I think that you can be very creative, especially as an auditor, on how you could use clean rooms. Let me give you another idea or an example. Let's say you wanted to monitor, just like I explained a little while ago, instead of the infrastructure health, you wanted to monitor the security health of a company. You could take all of your log data, put it in a clean room so nobody can have access to it, overlay on top of that the machine learning algorithms that can detect anomalies or irregular patterns of usage or irregular error message or alerts or events that are happening that are noted in your logs. And then you can look at that and you can say, okay, we've got all of these strange things happening over here. Why is that? And then you can work with security experts to say, oh, well, we understand why that's happening. And you can put on a rules engine that begins to help weed out those false positives and really zone in or narrow down so you have some very valid information that you can begin to dive into from a security perspective on real positives as the results. So you can be very creative about the data sets that you're going to be putting in a clean room, the machine learning algorithms, a rules engine that you might place on top. But it does require, getting involved, coming up with the ideas, and then seeing how you can peel back that onion to understand what's going on and to correct for any biases, like Shamim explained earlier. Make it as accurate as you can.
Yeah. So the
A quick question from the chat. Sorry for interrupting. Somebody was asking to clarify what the definition of a clean room is and where did it originate from?
So the general notion of a clean room is a computing environment that is protected and isolated with known entities and only known entities having access to the contents of the clean room. In particular, it is a set of executions in a certain computing environment that are isolated and protected.
I'll just add on when I talk about clean rooms, I think people normally think of the chip clean rooms where chips are manufactured and people have the white suits on to keep the room very clean from dust. But this is a data clean room. It's not a chip clean room. It's not a physical clean room. It's specifically for data. I think it's nice for me to refer to it as a data clean room, and that really clears up that misconception sometimes people have.
Yeah. It's a computing environment in which the access is controlled by the hardware that is in control of that particular computing environment, and access is based entirely on being able to a limited set of entities that are authorized and authenticated by the underlying hardware fabric.
I think it really is sort of a dream come true for auditors to be able to not have to do the same type of work in protecting the authorization and the authentication of people to data sets when there's zero access. The compliance with HIPAA, PHI, PII, even SOX to a certain extent largely falls by the wayside as long as the models are reviewed and shown to be correct, not biased.
I think we have a couple questions in the chat. I think had a follow-up question as to what regarding whether it was a sandbox or not regarding the clean room.
It's a sandbox in the sense that it's a computing environment. Some people have used the notion of a sandbox. It's a protected environment that is maintained at the hardware level in the case of confidential computing. So it is protected, isolated environment. The contents are hardware encrypted and are only accessible in an authenticated manner by using cryptographic means. So the security of the data clean room is based entirely on cryptographic features that are at the chipset level of the underlying hardware.
Yeah, I think the concept of a sandbox is more about how you find malware in a safe way. So the idea is you put an unknown file into a typically virtualized environment, and you explode that file, and you see if it's malware or not. It's a bit like, the bomb squad comes, and is it a bomb, real bomb, fake bomb? You put it in a big container that's bomb resistant, and you blow it up and you see, did it have explosives or not? But you can't really tell until you open it up. And so you're looking for the malicious software that might be embedded in, say, a PDF file or something. And so that's what sandboxes do traditionally in the terminology of cybersecurity. And it gets confusing because a lot of people will, intermingle terminology because they have similar notions of isolation, but when we get technical, it's the purpose behind it. So a sandbox the purpose is to discover malware or validate clean files and allow them to run to some other storage or other location for interaction. A safe room or a clean room or a data room are all things that are used to access important data in a safe way. So traditionally, for example, when I started out in this business, boards met in person, and then everybody would pick up all of the papers. They would do RF scans to make sure nobody was listening in. They would pick up all the papers after the board meeting was over and put them through a very, very expensive shredder that shredded them up into, pulp, essentially, because they didn't want any of that stuff to leak out. And I remember the first time I was involved in how the board members want all their stuff delivered to an iPad. And I thought, what? Oh yeah, it's so much easier. No, you can't do that. And then we're trying to secure iPads for board members, and because they were the first people who bought iPads. I mean, the first ones I ever saw were CEOs and presidents and members of boards of directors, and they wanted them to be in board meetings. How are we ever going to control that? Well, ultimately, the only way to control that is through encryption technologically, and so that's what, at some degree, Shamin and his team are doing.
Yeah. So it's a region of memory where your data happens to be. And that region of memory is protected by doing encryption. And the only process that can access is your process, which is authenticated to access that part of memory. So that part of memory is called the clean room.
I see another question in here. I'll read it to the group. For those auditors here today, where would you suggest that we start to have an intelligent conversations with folks to understand zero trust strategy and roadmap and what controls? So I would suggest that don't overcomplicate it. It sounds complicated, but keep it simple. You already audit many different things. You audit systems, you audit financial records, you audit logs. This is one more thing that you can audit, and you'll use the same techniques. So you'll go to your governance framework, COBIT or the other governance frameworks. You'll identify those things that are pertinent that need to be audited, and then you'll need to begin to discover who can provide evidence for your questions that they can attest to. And you can go about it in exactly the same process, but the people who you're dealing with and the things that you're auditing are a little bit different. And just try to keep it simple and basic. You'll be looking at the output of these, and you'll be looking for any breaches or oddities with respect to the output of the models from the data stored in the clean rooms.
Yeah.
And I just put in the chat the NSTAC report. So I was appointed to serve on the President's National Security Telecommunications Advisory Council Subcommittee on Zero Trust and Trusted Identity Access, which is a pithy title. But we delivered a report on what zero trust is, and it's on the CISA website. So we would consider that to be authoritative on what zero trust is. So review that first, especially focus on the 5-step model of zero trust. Define your protect surface, map your transaction flows, then figure out your controls and architecture, create your policy, because ultimately everything's instantiated in policy, and then monitor and maintain. Look at all of that data that's coming in, and this step 5 is really where we're going to see a lot of benefits from machine learning, AI, large language models, whatever you want to call it.